Hi, this is Dr. Habib Ahmed. Welcome to our in-depth tutorial on performing the analysis of gallium nitride HEMTs using Silvaco TCAD simulation with and without heating, that is, with and without thermal effects. In this video, we will explore the impact of temperature on the performance and reliability of gallium nitride high electron mobility transistors using the advanced tool of Silvaco TCAD. You will learn about a few things in this video. First, I will give an introduction to gallium nitride HEMTs, where you should be able to understand the structure, benefits, and applications of gallium nitride HEMTs. Second, I will tell you why thermal analysis is crucial. You will learn about the significance of thermal management in high power and high frequency devices. Third, I will demonstrate how to set up the simulation. I will give you a step-by-step guide to setting up the thermal analysis simulation for gallium nitride HEMTs in Silvaco TCAD. Fourth, I will show you how to run the simulation. I will demonstrate how to run the simulation with and without heating, that is, with and without thermal effects. And finally, I am going to tell you how to interpret the results. I will tell you how to analyze the simulation results to understand the thermal performance and identify potential hotspots. So first, let me tell you about a few basics of high electron mobility transistors and then about gallium nitride HEMTs. A high electron mobility transistor, also known as heterostructure FET or modulation doped field effect transistor, is a field effect transistor incorporating a junction between two materials with different band gaps. That is a heterojunction. For example, over here, if I zoom in on this structure, we have an aluminum gallium nitride material, this thin layer over here, on top of a gallium nitride material. So we basically over here at the interface have a heterojunction. And a high electron mobility transistor utilizes this heterojunction to demonstrate the field effect transistor. Now this is different as compared to the metal oxide semiconductor field effect transistor, in which we actually have a channel in which we have a lightly doped region, and we attract electrons from the bulk towards the channel in order to connect the drain with the source. HEMTs are used in integrated circuits as digital on-off switches. HEMT transistors are able to operate at higher frequencies than ordinary transistors and are used in high frequency products such as satellite television receivers, voltage converters, cell phones, and radar equipment. Now let me tell you about the significance of gallium nitride HEMTs. Gallium nitride HEMTs have attracted attention due to their high power performance because gallium nitride is a wide bandgap material. Gallium nitride based HEMTs demonstrate higher operating temperatures, higher breakdown strengths, and lower specific on resistances. And that's why gallium nitride based devices have higher Baliga's figure of merit and higher Johnson's figure of merit, which are basically the figures of merit for high power devices. A gallium nitride HEMT is a type of field effect transistors that utilizes the high electron mobility of this gallium nitride, aluminum gallium nitride heterojunction over here to achieve high speed and high power performance. Now here are the key components of this structure. So first of all, we have a substrate which is the starting layer. This substrate typically is either sapphire or silicon carbide or silicon substrate because of its compatibility with gallium nitride and lattice matching properties. Then if you focus over here, this thin green region is actually aluminum nitride nucleation layer. The nucleation layer, also known as the seed layer, is a very thin layer typically deposited between the substrate and the buffer layer. This layer is crucial in accommodating the lattice mismatch between the substrate, which is sapphire in this case, and the gallium nitride buffer layer. Common materials for the nucleation layer are aluminum nitride or low temperature gallium nitride. So even the aluminum nitride is relatively grown at a lower temperature if we want to use it as a nucleation layer. Then on top of the nucleation layer, we have the buffer layer, and it's gallium nitride in this case. A buffer layer is grown on top of the substrate to accommodate lattice mismatches between the substrate and the gallium nitride film that is going to be connected with the aluminum gallium nitride, which forms the heterojunction. Then sometimes we have a thin gallium nitride layer grown on top of the buffer layer, and this layer serves as the channel where the electrons move. The gallium nitride layer where the two-dimensional electron gas, over here we call it the two-dimensional electron gas because we form a quantum well, and inside the quantum well we confine electrons to 2 dimensions. We call it two-dimensional electron gas. So this 2DEG or two-dimension electron gas is formed, which is usually between these two undoped layers. Like this gallium nitride buffer layer is also undoped, and this aluminum gallium nitride layer is generally undoped. Now this layer ensures that the two-dimension electron gas is formed purely due to the polarization effects of the gallium nitride aluminum gallium nitride interface rather than the dopant atoms. Then on top of this gallium nitride layer, we have the aluminum gallium nitride buffer layer. This GaN layer is deposited on top of the gallium nitride layer. The difference in band gap between the gallium nitride and aluminum gallium nitride layers creates a two-dimensional electron gas at the interface, which is responsible for the high electron mobility. The aluminum gallium nitride layer is typically undoped or lightly doped n-type to enhance the formation of the two-dimensional electron gas at the interface. The polarization-induced electric field at the interface between the undoped gallium nitride and aluminum gallium nitride layers is responsible for creating the high electron density in this quantum well, in which we actually form the two-dimensional electron gas. Then we have the drain and the source contacts. These are ohmic contacts made to the two-dimensional electron gas region. And these contacts allow current to flow into and out of the two-dimensional electron gas channel. The regions beneath the source and the drain contacts may be heavily doped to form ohmic contacts. This heavy doping reduces the contact resistance and allows efficient current injection into this channel. Then in this structure, one of the key components is the gate electrode. It is a short key contact typically used as the gate electrode. The gate controls the current flow through the two-dimensional electron gas by modulating the electron density at this aluminum gallium nitride interface. So to summarize, we have undoped gallium nitride and aluminum gallium nitride layers. These could be lightly doped as well. We might have a lightly doped buffer layer, like the doping level in this layer is really low to reduce the leakage currents. And then we have heavily doped drain and source regions to form the contacts. Now this doping strategy ensures the criterion of a high electron mobility two-dimensional electron gas at the gallium nitride aluminum gallium nitride interface, providing the gallium nitride HEMT with its superior high power and high frequency performance. Now I'm going to demonstrate the simulation of this structure with and without heating, that is with and without thermal effects. Now, why do we want to see the thermal analysis of gallium nitride HEMTs? There are several reasons why thermal analysis is crucial for gallium nitride HEMTs. First, high power density. Gallium nitride HEMTs generate significant heat due to their high power densities. Effective thermal management is essential to prevent overheating and device damage. Second, reliability and longevity. Excessive heat accelerates material degradation, and thermal analysis identifies hotspots and informs cooling strategies, enhancing device reliability and the lifetime of the device. Third, performance optimization. Temperature impacts electron mobility, threshold voltage, and leakage currents. As I'm going to demonstrate that when we apply heating to the device, the threshold voltage increases and also the drain current characteristic deteriorates. So thermal analysis helps optimize the device performance under various conditions. Fourth, it's crucial for preventing the thermal runaway, which can cause self-enforcing overheating. Thermal analysis helps design HEMTs to avoid this risk as well. Fifth, efficiency improvement. Understanding thermal behavior leads to better cooling solutions and material choices, improving the overall device efficiency. Sixth, thermal analysis guides the choice of the substrate and materials, ensuring better thermal conductivity and stability. And then seventh, we can integrate these devices with other systems. So thermal analysis is crucial for the overall system stability. Eighth, effective thermal management reduces the need for expensive cooling solutions and increases efficiency, leading to cost savings. So, thermal analysis is essential for managing heat, ensuring reliability, optimizing performance, and guiding material choices in gallium nitride HEMTs. This approach results in an efficient and reliable device for high power applications. Now, with that basic introduction, let us start talking about the code part now. So for some reason my mouse is stuck. Okay, so now that I have enabled it, let us move to the code part now. Okay, so here is the code for high electron mobility transistor for gallium nitride HEMT. I start with Go Atlas, and then I introduce the meshing for the high electron mobility transistor. My structure is running from 0 to 10 micrometers in the X direction, as you can see over here. Let me reduce the size of it so that we can see the code and the structure side by side. Similarly, my structure is running from 0 to 3 micrometers in the Y direction. My region number 1 is sapphire, running from 0 to 10 micrometers in the X direction and from 2 to 3 micrometers in the Y direction, as you can see over here. Then my region number 2 is aluminum nitride nucleation layer, running from 1.98 to 2 micrometers in the Y direction. So basically this is a 20 nanometers aluminum nitride nucleation layer. Generally, the aluminum nitride nucleation layer is really thin in actual devices as well. Region number 3 is gallium nitride buffer layer, running from 20 nanometers to 1.98 micrometers. So this big region over here is my gallium nitride buffer layer. Then I have the aluminum gallium nitride layer over here forming the heterojunction with this gallium nitride layer, and the aluminum content in this aluminum gallium nitride is 30%. After that, I have introduced the electrodes. So my source is running from 0 to 0.5 in the x direction. This is the source region, and from 0 to 0.2 micrometers in the y direction. Similarly, I have introduced the drain over here, running from 9.5 to 10, and from 0 to 0.2 in the y direction. Similarly, I have introduced this gate electrode, running from 4 to 6 micrometers in the x direction, and then I have introduced the substrate. Then I save the structure, and I start working in another module of Atlas Silvaco TCAD, where I call the previously saved structure. I've saved it with this name, and I call it in the other module of Atlas Silvaco TCAD. Here I define the work functions for the gate, for the source, and for the drain. Then I define different models. The print model, for example, which tells us the runtime status of our simulation, then the Shockley-Red-Hall recombination. This model over here enables the mobility model. Then I have introduced polarization in strain models. This enables automatic calculation of the interface charges due to spontaneous and piezoelectric polarization, the polarization part. And this calc strain actually specifies the strain in the region calculated from the lattice mismatch with adjacent region. Then we have this parameter, polar dot scale, which specifies the Carnot scale factor multiplied by the calculated spontaneous and piezoelectric polarization charges, and it's basically about the polarization in wurtzite materials. Now in HEMTs, what happens is that the electric current flows between the drain and the source element via the two-dimensional electron gas, which is located at the interface between the aluminum gallium nitride region and the gallium nitride region. Now let me show you why we call it the quantum well, which results in the two-dimensional electron gas. So for example, we go to tools, cut line, we draw a cut line across this interface, and then we go to display. So the conduction energy level, valence energy level, electron quasi-Fermi level, we hit apply. So now you see a slight kink over here at this interface between the aluminum nitride and gallium nitride layer. This actually confines the carrier to a two-dimension. That is why it's called a two-dimensional electron gas. Also, I want to see the electron concentration. So even you can see that even under thermal equilibrium, the carriers are actually confined to this quantum well, to this two-dimensional electron gas channel. So a two-dimensional electron gas occurs when electrons are confined to an interface between the aluminum gallium nitride and the gallium nitride layer. HEMTs make use of high mobility electrons generated using this heterojunction, which is created by the aluminum and gallium nitride and gallium nitride layers, resulting in a quantum well. These electrons can move quickly without colliding with any other impurities, and this quantum well, and these electrons cannot escape from this quantum well. The effect of this is the creation of a very thin layer of highly mobile conducting electrons with very high concentration, giving the channel very low resistivity. Or in other words, you can say high electron mobility, and that's why you call it high electron mobility transistor. So why are the polarization charges created over here? Due to two effects: the spontaneous polarization, which is due to the hexagonal structure of the gallium nitride and aluminum gallium nitride. There is a natural asymmetry in the hexagonal structure of the gallium nitride and aluminum gallium nitride layers, resulting in spontaneous polarization. Then aluminum gallium nitride and gallium nitride layers have a lattice mismatch, resulting in a piezoelectric polarization. And the combined effect of this spontaneous polarization and piezoelectric polarization actually results in polarization charges. So that's where the charges actually come from. Then we want to look at different output parameters, the energy levels, the current flow lines, etc. I have employed the Newton method for the numerical calculation of my semiconductor HEMT device. There are several numerical methods. There is a Gamal method, there is a Newton method, there is a block method. The Gamal method is useful where we have linear convergence. Similarly, the Newton method is useful where we have quadratic convergence. The Newton method, however, spends extra time solving your results, so keep that in mind. And also the Newton method requires a more accurate initial guess. Now the thermal analysis actually takes a longer time, so we are going to use block method when we work with the thermal analysis, because block method can provide a faster solution for the simulation of these devices over the Newton method. So the way I've structured my code is, initially in this first module of Atlas, I create the structure. Then in this second module of Atlas, I actually perform the drain current characteristics of this HEMT without heating. And then I also have defined a third module of Atlas Silvaco TCAD where I perform the simulation of this HEMT device with heating effect. So in this second module, we don't actually need to include a heating model. We are going to include the heating model in the third Atlas module. You also see the max trap. This actually defines a procedure repeated up to a maximum number of tries set by the method parameter, and once the convergence is obtained, the bias steps are then further increased. Like for example, over here we have introduced 20 number of max traps, which is actually 20 number of tries. If the program comes across any convergence problems, it's going to give it up to 20 number of tries. Then over here we find an initial guess into the structure, then we save the structure with this name, and with Tony plot command we plot the structure with this name. Now I want to look at a family of current voltage characteristics. First, I want to look at ID versus VGS characteristics without heating. So I have set the drain voltage at 5 volts and I'm ramping up the gate voltage from minus 20 to 0 volts initially, and then from 0 to 1 volts. So basically I'm ramping up the gate voltage from minus 20 volts to 1 volt. So for that purpose I actually create a log file with this name, and then finally I plot the structure under this condition, and then I also plot the log file. This will give me ID versus VGS characteristics without heating. Now I want to look at ID versus VDS characteristics, or the drain current versus the drain voltage characteristics at different gate voltages. So for this purpose I'm employing 4 different gate voltages: a gate voltage of minus 6 volts, a gate voltage of minus 4 volts, a gate voltage of minus 2 volts, and a gate voltage of 0 volts. And at each of these gate voltages I've ramped up the drain voltage from 0 to 30 volts. I create log files for this purpose. Then I save the structures under these conditions at each of these gate voltages, and then finally over here I plot all these log files at different gate voltages excuse me, using this overlay command over here. So at this point you will see that we would have performed the simulation for the ID versus VGS characteristics, and also ID versus VDS characteristics for the gallium nitride high electron mobility transistor. Now in the third and final module of Atlas Silvaco TCAD, I want to look at the family of drain current characteristic curves with heating, that is with thermal effects. So once again I start this Atlas module and I call the previously saved structure. I define the work functions. Then I introduce the models. These are the same as the previous models, but at this point I'm going to add one more model, and that model is this lat.temp model. So this model over here actually enables the heat flow simulation, and once I introduce that model, what I'm going to do is I apply a thermal contact to my structure at y is equal to 3. So my structure is running, if I zoom it out, my structure is running from 0 to 3 micrometers. So what I'm doing is I'm applying a thermal contact to the bottom of the structure for thermal heating of my device. Then once again the rest of the structure is going to be the same. I want to look at some output parameters. I've introduced the Bloch and Newton methods for the numerical simulation of my device. Then in this section I actually want to look at the drain current versus gate to source voltage. So I've set the drain voltage at 5 volts and I'm ramping up the gate voltage from minus 20 to 1 volt. Similarly over here I want to look at the ID versus VGS characteristic curves. So I have set the gate voltage to minus 6 volt and I am ramping up the drain voltage from 0 to 30. Similarly I have set the gate voltage to minus 4 and I am ramping up the drain voltage from 0 to 30 volts. Similarly I have set the gate voltage to minus 2 volts and I am ramping up the drain voltage from 0 to 30 volts, and finally I have set the gate voltage to 0 volts and I am ramping up the drain voltage from 0 to 30 volts. And finally I overlay these curves into a single figure. So at this point we are ready to run the simulation. Let's do that. here is my structure under thermal equilibrium, and if we right click on the structure, then click on display and click on this icon to enable the contacts. So to enable, basically to be more accurate, to enable the labeling of the contacts. So now you can see here is my drain contact, here is the gate contact, and here is the source contact. And we also have the substrate contact over here. We have a slightly darker layer, so you might not see it. It's not really highly visible, but if you focus, it's still visible. Then you can also see, if you right click on the structure and click on display, you can also see the meshing by clicking on this icon. So we have introduced a denser meshing in this region, which is our region of interest, because we have the two-dimensional electron gas formation across this aluminum gallium nitride heterojunction. And also we have a relatively denser meshing at this interface, where we have the interface of the buffer layer and the nucleation layer, and then another interface of the nucleation layer and the substrate layer. Then we can also see the energy band diagram of this structure under thermal equilibrium by clicking on tools, then cut line, and we draw a cut line across this interface. We right click over here, click on display, and then we click on the conduction energy level, the electron quasi-Fermi level, and the valence energy level. Hit apply. So here is the energy band diagram under thermal equilibrium, and you see this slight kink inside this energy band diagram. So because of this heterojunction between the aluminum gallium nitride and gallium nitride layer, we see this the formation of this kink in the energy band diagram, which basically confines the carrier to a two-dimension, hence called two-dimensional electron gas. We can also see the confinement of these electrons by clicking on polarization, charge concentration. So yeah, so you see, like, the polarization charges are actually confined to this interface between the aluminum gallium nitride and the gallium nitride layer. Now the program has simulated this part of the code, which actually gives the drain current versus gate voltage characteristics at a drain voltage of 5 volts. So we see that our threshold voltage is around, I would say, roughly minus 6 volts. For this structure where the aluminum gallium nitride layer is 20 nanometers, and we have a 30% aluminum content in the aluminum gallium nitride film. Now what does it mean? So we can use aluminum gallium nitride HEMT as a high power switching device. So, and it means that in order to turn off the device, we need to apply a voltage of minus 6 volts to the gate of this structure. Now let me minimize this one. Now here is the structure at a gate voltage of minus 6 volts. So actually this structure comes from this section of the code over here, where my gate voltage is minus 6 volt, and I'm sweeping the drain voltage from 0 to 30 volts. So So there is some crucial thing like which we can look at. For example, we go to display, then we click on contours, go to define contours, and here I want to look at the current flow lines. And then hit OK. So now you see we can further focus on this from 0 to 0.8 micrometers in the vertical direction. So basically what is happening, this HEMT device is a normally on device. When we apply a negative voltage to the gate, it actually repels electrons away from the channel over here under the gate electrodes. So at higher negative gate voltages, if we don't form the channel, the drain and the source are not connected, and hence the device is turned off. But at this voltage of -6 volts, we just form the channel. It's the threshold point of the device, and we have a reasonable current flowing across the device. Then if you focus over here, this is actually the same structure at a gate voltage of -4 volts. So once again, if we go to display contours and then look at the current flow lines, so not conduction band energy but the current flow lines, and hit apply. So now we see that at -4 volts there is a slight less repelling of the current flow lines under the gate electrode as compared to at -6 volts. And then we have similarly the structure at -2 volts as well, as you can see from this label. So at voltage of -2 volts, once again we go to display, and then we go to contours and we look at the current flow lines, hit apply. So now you see that now the current flow lines are even less repelled as compared to higher negative voltages. And finally we also have the structure at 0 gate voltage. So at this point we go to display, we go to contours, we define contours, we go to current flow line, hit apply, and we see even smaller repulsion of these current flow lines. So now actually the channel is formed and the current can easily flow at higher positive voltages between the drain and the source. Similarly, we can also look at some other parameters. For example, we go to display and then we go to contours. Instead of current flow lines, we can also look at the current density, for example. So the total current density. Click OK, and if you zoom in on this region, now you see that the current density is actually confined to this thin channel, which is the junction of the aluminum gallium nitride and gallium nitride layer. Similarly, we can go to display once again, contours, to see the polarization charges, and click OK. And now you see that the polarization charges are actually confined to this heterojunction, to the quantum well, also called the two-dimensional electron gas. So similarly, you can see the potentials across the structure and a lot of other things displayed over here. Like for example, if you want to look at the potential, so you click on this. Okay, and we zoom out the structure. So here is the potential across this device. Okay, I'm gonna close these figures now. And now at this point I'm interested in looking at the drain current versus drain voltage. So we go to display, and instead of the gate voltage I select the drain voltage, hit apply and click OK. And here are the family of curves for the drain current versus the drain voltage. This one is at a gate voltage of minus 6 volts. The red one, the green one, is at a gate voltage of minus 4 volts. This blue one is at a gate voltage of minus 2 volts, and this cyan one is at a gate voltage of 0 volts. So if we go towards more positive voltages, we see higher drain currents versus drain voltage for this GaN HEMT structure. And now that we have seen these family of curves, the program has started running the final module, and it has run the drain. It has run the drain current versus the gate voltage characteristics, this block, at a drain voltage of 5 volts under heating now. So if you compare these two, you might see, like let us bring these two side by side. So this one on the left is actually the ID versus VGS characteristic curve for at a drain voltage of 5 volt without heating, and this figure on the right is ID versus VGS at a fixed voltage of 5 volts VDS with heating. So as you can see that without heating our threshold voltage is around minus 6 volts. And with heating, our threshold voltage has increased to, I would say, minus 7.5 volts. So that is a big increase. There is a big increase in the threshold gate voltage under heating. And now we are running the ID versus VDS, or you can say the drain current versus the drain voltage characteristics at fixed gate voltage of minus 6 volts, minus 4, minus 2 and 0 volts, where the drain voltage is ramping from 0 to 30 volts. Now the thermal analysis or the thermal simulation of this device takes a really long time. It's going to keep running for the next 20 minutes, and I don't want to make you wait for that long. So I actually saved the ID versus VDS characteristic curves with heating for this HEMT structure as well. These are the ID versus drain current versus drain voltage characteristic curves at gate voltages of minus 6 volts, minus 4 volts, minus 2 volts, and 0 volts. And if you compare it to the family of drain current versus drain voltage characteristic curves without heating, you might notice that there is actually deterioration in the drain current if we include the heating effect in the device as well. Like, the first thing you might notice is that the current levels with heating are much lower as compared to the current levels of the device without heating. Also, you might see over here there is deterioration in the drain current versus drain voltage as we keep increasing the drain voltage. So you might see that around 10 volts we start seeing the deterioration in the drain current versus the drain voltage under heating of the gallium nitride HEMT device. One more thing that I might have forgotten that I want to tell you is that we are looking at the thermal analysis of the gallium nitride HEMT, but what is the temperature that we have applied to this HEMT structure? And I actually forgot to mention that. So in this case, for the thermal analysis of the gallium nitride HEMT, I have set the external temperature to 300 Kelvin. But you can further increase or decrease this temperature to perform the analysis, thermal analysis of gallium nitride HEMT for your own specific application. That's it for the simulation. Don't forget to subscribe to our channel for more tutorials on semiconductor devices, Silvaco technology computer aided simulations, and advanced electronics design. Please like, share, and comment. If you found this video helpful, please give it a thumbs up, share it with your peers, and leave a comment below with your thoughts or questions. I love hearing from our community. Take care. Until next time. Adios.